don't let me continue on past 440. As soon as 440 hits, we'll finish, okay? 40. Goodness sake. Right, so interference now.
Recording is working.
Recording is working. Everything is working. We're in business. No, that should be good for another 3 or 4 years. Okay. Waves, interference. Nice. Okay.
It worked very well.
Oh, so well.
Too fast.
Too fast. Look at the speed on this.
Yeah.
Do you know this has a gig of RAM? 1 gig of RAM. A whole gig of RAM, yeah.
1 gig RAM.
1 gigabyte of RAM. Can you believe that?
Oh.
A whole gig.
Oh my god. 1 gig RAM, only 1 gig RAM.
No. A full gig. Yeah? Yes.
10 years ago.
True. Okay. Just loading the PowerPoint into memory as well. Right, let me plug my writing pad in actually. So, what we're going to have a look at now. One moment, please. Oh, sake. No. Are you sure you want to quit? Yes, I shouldn't use this program. I should use just a regular program. It'll be fine. Adobe is too bloated. Okay. I am always careful. Presentation. Interference. Oh, sorry. Interference. We can write that down.
Interference pattern.
Interference pattern, yeah.
Quantum physics.
Yes! Yes. Are you excited about your active listening?
Yeah. No. So exciting.
No, there'll be science in it. Trust me, you'll see. Okay, interference. So, we might have to split this into 2. We'll see how we get on. Right, so actually, you might already know this from your quantum physics. What is interference of waves? Go on, yeah. No, make the hand gesture again, but add in sound effects. Go for it. No, go for it, let's see.
What is that?
I know sound effects. Yeah, go on. So what happens?
When 2 waves come together.
Yeah, now you've got a sound effect.
Vroom.
Yeah, 2 waves come together and what happens? A new wave, bigger, yeah, or it could actually be smaller. The wavelengths, the amplitudes add when they meet, the heights add. So interference is when 2 or more waves combine to form a new wave. And the principle of superposition states the new amplitude at each point is the sum of the amplitudes of the individual waves. So just before you write that down, let me just draw that as a picture. Here's the first wave. And then here's the second wave. We'll make it blue then. And we add these 2 together. So if I want to know, say, here, what wave do I get at this point, all I do, oh sorry, that's a stupid wave. I take this height from here to here and add it to this height. So because this is negative and this is positive, and this looks like it's bigger than this, should my new wave be above or below here?
Below.
It'll probably be below then. Like here's the simple example that's usually in the book. You have a wave like this, and then you have a smaller wave like this, and you add them together, and you get a wave that looks like this. like this. Yeah. What's happening is you add this height to this height. So because this is much bigger, it means it mostly keeps its shape, except these little heights add and subtract as you move along. So this is what I mean when I say the net amplitude at each point is the sum, the addition, the sum of the amplitudes of each wave. Now, you need to copy this word for word. Those words are very important: interference and principle of superposition. Wilkie, what happened to your lovely tea flask, the pink one?
I changed it.
Ah, you shouldn't have. I liked it.
Do you like it?
Maybe.
Because it is bigger than that.
Okay. There's no colour.
Yeah, I have color. Clean. And then blue.
Yes. Okay, do we nearly have this? You have this, Calvin, do you? Yeah. You have this? Yeah. Who am I waiting for then? Nobody? Did you know these words because you learnt them when you were reading for the practice active listening, or did you only learn them because of the active listening? I mean, how did you come across interference for the first time? In the reading or in the listening?
Reading.
The pre-reading.
Yeah.
Huh? And this is something you know from high school as well then, yeah. Continue? Yeah. So, basically, the heights add or subtract. Simple as that, really. And oh, there's the example I was drawing for you earlier. Yeah. So, what is meant by coherent? I wonder if you know this one from school. Two waves are coherent if. Do you know this one? Yeah.
Same phase.
Yeah. What's phase though?
Same.
Huh?
Same. You know?
Definitely need to be the same frequency. Yeah. Two waves are coherent if they have a constant phase difference, which we'll explain, and the same wavelength, or is it technically the same frequency? I see some definitions that say wavelength and some that say frequency. What did you use in high school? Yeah. Anyways, I think we should really say wavelength, I think. But we have to now say what I mean by phase difference is constant. Does anybody actually know what the phase difference of a wave is? I think actually, did I not say this in an earlier lesson, the phase difference? I think I did. Because I remember we had the symbol for it, the phi. Yeah, so I did mention this in a past lesson. Do you want to see it in your notes? Check for phase.
Pi? We didn't.
No, phi.
Phi.
And please check your notes for phase difference. Phase.
We have?
Sure you do. You have, very good, yeah, you found it. What is it?
The time difference between the crest of two different waves moving together.
That's it, yeah. So, the...
Boom, boom, boom.
Yeah.
Same boom, boom, boom.
Same boom, boom, boom.
Yeah.
This is, I mean, this is really just like, I don't know, South Korean pop, is it? Like Gangnam Style, boom, boom, boom. Same, bum bum bum.
Different.
Okay, so you're confusing me now. Right, let me just move this here a little bit.
Yeah.
Okay, so if you look here, here is the peak here, and here is the peak here, and there's a difference obviously between them. And here is the peak here, and here is the peak here. And in my example, this here, well, in the picture I drew, it's not the same. It's actually getting smaller. You can actually see here in my next picture, they're nearly the same now. So there's the peak there, there's the peak there, and there's the phase difference, the difference between the peaks. Coherent means that the phase difference is constant, that it's not changing, that they stay the same distance apart, and also that they have the same wavelength. This is the meaning of coherent.
That means they are twins,
Kind of, yeah.
but different time to start.
Yes,
Twin, but different time to start.
yes, like real twins, I suppose.
Absolute twin or singular twin.
Depends on the book, I think. For us, we mean absolute, because our waves always look the same. They go up, down, they're nice and smooth. So we'll say absolute. Or identical.
Yeah.
Okay, did you write this definition down? Note, the last definition I haven't really seen on the exam. I don't even know if I've ever seen it on the exam. But this definition I've seen on the exam a few times, which is good because this definition is shorter. So can you make note that this is a more common definition than the last one? I've only given you two definitions, so more common than the last one. Yeah? Continue? Yeah? Okay, so here's a nice picture to show you this. The distance here between the peak, the fudge, here's the peak here, and here's the peak here. The difference is a constant. It stays the same. This peak and this peak, same distance apart. Yeah, you can see that okay? That is coherent waves. They're coherent. Yeah? Okay. Now, when two coherent waves propagate together, what does propagate mean for waves?
Spread.
Yeah, spread, move.
Yeah.
From two different sources, and they meet, then we say the path difference is the difference in the wavelength each of them travelled. And we express this as a multiple of the wavelength. Now, before you write that down, let me explain what on earth I mean by that. So, let's imagine we have something here where the waves meet. And let's say one starts here and one starts here. Okay, so here's the first wave. It goes up, down, up. And you know what? Actually, I'll make this one here closer. Okay. Up, down, one cycle. Second cycle. Third cycle. And it finishes on the fourth cycle. Now, let's say this wave here is coherent. In fact, let's make it identical. It starts at one cycle. 1, 2, we'll say. Now, which wave has travelled further, the first or the second? The first one has travelled further. Yeah. But when we talk about waves that meet, we don't care how far they've travelled. We care when they meet how much of a wave difference is between them. What I mean is, this wave finished at the end of a cycle, you know, 1 cycle, 2, 3, and 4. And this one was 1 and 2. It finished at the end of a cycle as well. So we actually say the difference is 0. Let me give you a different example when the distance is not 0 to make it clearer. So let's say this wave was like this instead. 1 2, but then when it gets to here, it travels a quarter of a wave when it gets to this sort of endpoint. So in this example, the first wave completed a cycle, the second wave was a quarter of the way through the next cycle, so we say the difference is a quarter of the wavelength. So what we care about is the wavelength difference, not the total difference. That's what we mean by when we say the path difference. So it's always some number times lambda, and that number must be smaller than 1. It shouldn't really be more than 1, because we only look at one wavelength, because if it's 2 wavelengths, we're into the next wave and we should start again. So this one's a little bit difficult, but this one here, look at my picture. You see here the path difference is 0 because both waves finish at the end of a cycle. Kind of hard to see here. In this picture, the path difference is half a wavelength because it's really hard to see. But the top wave, let me see, up, down, up, down, up, down. I think it's at the bottom, and this one here is up, down, up, down, up, down, up. I think there's one finishes on a crest and the other finishes on a trough. So there's a half a wavelength between that. Okay, this is path difference. This is actually very important in waves when they combine. So if you can write this down, you don't need to write that part down. I think that's enough. If you just want to get that much. No, write it down, Wookie. It's okay.
No, but if the S1 is finished at the half,
like in the middle.
Yeah, middle.
Yeah.
And the second one is finished at the quarter.
So then it's a quarter.
Yeah.
A half minus a quarter.
Half minus quarter.
Half a wavelength minus a quarter of a wavelength is a quarter. So you mean maybe if one wave finishes at 3/5,
Yeah.
and the other one finishes at 1/5,
Yeah.
then the path difference is 2/5.
2/5.
Yeah.
Okay.
But
Remember this definition?
look deep inside your heart. What do you think? No, deeper. Look deeper. In seriousness, though, this isn't the type of definition in the exam that they usually ask students to recite. This is more just a definition so you understand this meaning when they use it in a question, like as a term. It's not the type of definition that they might actually ask you to define. Some definitions are really good for the exam, like what is a Newton or what is Newton's second law or whatever. You know, these are like good exam
What is
definitions.
the conservation of energy?
Yeah, all this stuff. Yeah. Did I ask you that one?
Yeah.
Ah, nice. That's very kind of me. Very kind of me. I think I asked you Newton's second law.
It's your market, yeah.
Good one. Oh, sorry, you're being serious. I shall begin tomorrow. Yeah, tomorrow sounds good.
Begin tomorrow.
Oh yeah, that sounds better than beginning today. Yeah, you understand. Yeah. Okay. We got that? We can continue? Yes? Yes? Okay. So, this is important because it gives us two types of interference called constructive, and these is when the waves combine to form a bigger wave. But more interesting is destructive, and these are when the waves combine to form a smaller wave. And it's actually possible to have something called completely destructive, which is the most interesting of all. What do you think happens here?
Zero?
Yeah,
Flat?
that the waves combine to cancel each other. So this is completely destructive and this is completely constructive. So this is completely constructive because the two waves perfectly add together to become perfectly twice as big. But this is completely destructive because the two waves perfectly cancel. Now, this is actually very, very useful, and there is something, there's actually a few applications of completely destructive, and there is something that I think maybe some students might already have at home or at school that makes use of this technology, this completely destructive interference. And it has something to do with sound waves. If you think about something where it's important to have destructive sound waves, you would like one sound wave to cancel and destroy another sound wave. Can you think of anything you might own that uses this technology, this physics?
My sister loudly word,
Yeah?
and my another sister loudly word bigger than.
Ah, yeah, but you want something you own that uses this. So you're thinking of constructive. You have two sounds and they
Yeah.
combine together
Yeah.
to make a louder
Yeah,
sound.
yeah.
I'm talking about destructive. You have two sounds and they combine to make a quieter sound.
It's not a lot of that, but I think in police station,
Yes? What do you think?
when they make a block the sound,
The sound?
it's the same.
It could be. I've never been in a police station, but it seems you have. Tell me what happened last time you were there.
I saw the movies.
Ah, sure. Movies. Yeah. I don't know what this is in the police station, although there could be something in the police station. I'll give you one example. Does anybody have noise-cancelling headphones? This guy, you have noise-cancelling headphones, do you? Yeah. Do you know these headphones? Noise-cancelling? Do you have them with you? No, okay. So these headphones, what they do is, there's a small microphone on the outside, and this microphone picks up the sound that's coming to you, and it takes this sound wave and it makes the opposite of it and plays that in your ear. So it has the effect of cancelling the sound coming from the outside world. Okay, these are like new headphones, these noise cancelling headphones. They use destructive interference. Do you find that it works well, or is it not working so well? Like, can you hear so much outside?
Not really.
It works pretty well, does it? Good, okay.
But it's not completely, it's not 100%.
Yeah, it's going to be hard to make it 100% because you would have to have a very good microphone and a very good sort of computer chip to make the cancelling sound. But what percent would you say it can cancel? If it's not 100%, what would you say?
70%.
Oh, okay.
7%?
No, 70.
Okay.
That's a bit disappointing. I was hoping it could do better than 70 because I was thinking of buying some actually. Okay, well still 70% if you think it can cancel. Yeah. Another example. When you look into the sky, you can see a plane and you can hear it, right? Even though it's very, very, very far away. When you're on the runway, about to get on the plane, you can hear the engine. It's very, very loud. Yes. It's very difficult to actually talk to your friend if you're on the runway when the engine is on. But when you're on the plane, can you talk to the person? Yeah. Even though you're actually closer to the engine, you might only be 3 or 4 meters from the engine, but you can still talk. So the plane is actually using destructive sound waves to cancel the sound of the engine. So even though you're very close to the loud engine, you can actually still talk quite easily.
Amazing.
It is, isn't it? I think it's very, very interesting.
Oh
The
my God.
same thing happens in factories as well. To make, factory noise. Yeah. In a good factory, okay? Not one of those factories you see on the news in certain countries that rhyme with Schmeiner. Yeah.
Amazing.
Okay. Yeah. No? Yeah. I wasn't being that subtle about it. The good factories that want to protect the ears of the workers would use technology like this to cancel the sound from the machines. So I think this is very interesting that you can actually cancel the sound wave. But it's not just the sound, it's any type of wave you can cancel if you can produce something which is the opposite. When there's a peak, when there's a crest, there's a trough, and when there's a trough, there's a crest, a peak, yeah. Okay, can you write these down, constructive and destructive? If you write something down, please. Oops. Yeah. You've seen this before? Yeah. Where did you get your headphones from? Yeah. That's where I saw them when I was looking online, the cheapest place for them. Were they a good price?
How much?
Let me just put it this way, more than or less than 100?
More than.
More than or less than 200?
More than.
Oh, I'm getting scared now.
What?
I don't know if I want this. More than or less than 300?
More than.
Oh no, don't talk to me.
Oh my God.
This is too much for me.
So there's 10% off there.
Oh, well then, 10% off, okay. I'm kind of scared to ask the next question. More than or less than 400? Oh, good.
30 something.
Good.
Oh, it's expensive.
It is. That's actually more than my laptop, by the way, FYI. I paid, I got this 4 years ago. Cost me $299.
299.
Yeah.
No discount.
No discount, no. No.
299.
Yes.
299.
€2.99.
299.
Yeah.
Found it in the bin.
Yeah, somebody gave me €3 to take it.
Good deal.
Yeah, it was a good deal, yeah. Okay, continue. You got that? Yeah. Can you think of any other examples where destructive interference might be useful?
The new car.
Ah, very good, actually, yeah. You could maybe use it inside of a new car to make a quieter driving experience, or a racing car. Although I don't think they put in the racing car because they want to reduce the weight. So I think they would just let the driver suffer. Do you know which cars actually might have this in it? No.
Bench.
I would imagine it would kind of be the fancy cars, maybe. You know, like the what do they call them? The you know, the like the business type of cars.
Rolls Royce.
Yeah, but what's that type of car called?
Sedan.
Executive car, you know, like the Rolls Royce, the sort of the cars that are more focused on a comfortable journey than performance, like Rolls Royce or something like this. Yeah.
Expensive.
Yes, very expensive. Okay. We know this, don't we?
Physics.
Yes. Yeah.
Oh my God.
Looks familiar, doesn't it?
Yeah.
So, Young actually performed this experiment with light a long time ago, and when he, maybe like 300 years ago, 400 years ago, when he shined light between two slits, it actually made this pattern here on the wall. And we want to see why we get this pattern. Because you might think two holes should mean two lights, but it's not. So, let's do our very, very, very best to explain this, and then I think, we'll probably finish on this. So, I'll try and draw it, and then you can try and draw it. So, let me do my very best. Right. This is our light. And then our light has two slits. And then we have our screen here. Now, when Young did this experiment, he just used a little hole in the window, he covered the window in paper and then put a little hole in it, so only a small little light source would come through. And then he put in front of that a piece of paper that had two slits cut through it. And let's see what happens. So, I'm going to use red for crest and blue for trough. Okay, so we'll go crest, 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 and in between the crests, trough and trough. Okay, so crest, 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 and then we have trough, 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 trough and trough. So it's really, really hard to picture this, but these waves are moving together and they're colliding and they produce this pattern. What will this pattern look like? There will be some places where the two crests have come together and formed a larger crest. There's some places where the troughs have come together to form a deeper trough. But interestingly, there will be some places where the crest will meet the trough, and what happens here? Cancel, which is flat.
Yeah.
No wave here. So if I try to continue drawing this, which will be very hard. Oh, good grief. Here will be cancel, and here is cancel. So if you were to follow, if you imagine you're walking along here, will you be walking on a crest or a trough of a wave? Nothing. So here, will there be any light? There will be no light. But if you imagined you were walking along this, here you would have light. Now you can continue this pattern, and what you'll discover is you'll get something that looks like this. Something which is very bright here, then you have darkness, then you have another bright spot, but it's not as bright. Then darkness, then another bright spot, but it's not as bright, and so on. And likewise in the other direction, brightness, but not as bright, brightness, but not as bright. And this image here is called interference pattern. This is Young's double slit experiment, and this is called an interference. Oh, flip it. Oh, fudge. Okay. Interference pattern.
The level of darkness is same.
Yes, because dark is dark.
No.
I know. No, it's dark. It is dark. It's the same. Yeah. Huh?
So the light gets
Yeah.
Does it get like completely dark?
It does. Yeah, it doesn't continue forever. It will reach a point, and then after that, there's zero light, and we'll actually calculate that limit as well when we cover this later more. I mean.
How is it getting dim?
You're going to make me draw all my waves. Basically, what's happening, you can imagine that the reason this is the brightest is because as the wave spreads out, it dissipates. Do you know this word, dissipates? Yeah, but also not only does it spread out, but in some sense it reduces. It's a bit like, as I'm speaking, we understand that the wave is further away, there's less amplitude because it's spreading out, it's dissipating. So that's actually what's happening too. Also, I have a feeling that you're going to have maybe more waves that can combine in the center than out at the end here. What I recommend that you do, there's a wonderful animation, I think it's on Wikipedia, where it can show you this in 3D. You can see like the waves, their heights combining, and you can actually see the large combinations in the center and then the smaller combinations at the end. So if you actually Google this, you can find a nice little 3D animation that can show you much better than my picture of how these are combining. I think I saw it on Wikipedia, but I'm sure you could see it on YouTube as well. Yeah.
Light spots are because of constructive and
Yes, and the dark ones are because of destructive. Yeah.
it doesn't matter if it's a crest or a trough.
Oh no, it doesn't actually, which kind of seems strange, doesn't it? It feels like this should be two troughs combined, but no, it's when a crest combines with a trough. Because having a crest or a trough is good, it means you have light. It's only when it's flat that you have no light. So yeah, here is destructive, this is constructive, destructive, constructive, yeah. Yeah, so, I mean, this could be caused by two troughs or two crests coming together.
To crest.
Or two troughs. I mean, the only difference with a trough is just, it's upside down.
Yeah.
It's the same thing. Like, if you're on an ocean wave, this is the ocean, and you're here, or you're here, both are scary. You don't care if it's up or down. You're at the top or bottom of a big wave. It's both a problem. You're only safe if you're on a wave that's like this.
Yeah,
true. Do you want to try and draw this?
I don't know.
No? Well, I see some people are being brave and drawing this, and I applaud you. Oh, very good, you drew it. You drew it. You're too scared to draw it.
Yeah.
Yeah, okay.
True.
You drew it.
I draw in my brain.
Yeah, that doesn't work in the exam though. It's a problem. The only reason I think it's Samsa and not Shamsa is because there's a coffee shop in my town called Samsa. I think so, yeah. I don't know. Yeah. Okay, we got this. Continue? No, I said we finished there, so we're finished there.
How many more slides?
How many more slides? Halfway there, I'm afraid. Yeah. Alright, let me close this.
So we don't have homework.
Yeah, you happy? No homework. Freedom, yeah.